Hey, how's it going today? Quick little note here. I have computer science students sometimes who leave the program because they don't like calculus, and they talk to their friends, and their friends or their teachers sometimes tell them, if you do computer science, you're not going to need calculus, right? You're never going to use calculus again after school. And so they don't feel like they should take calculus, and they end up leaving computer science and doing something different. Um, and it's true, as a computer scientist, you sit down and you write code at a keyboard all day, right? You're not solving equations that involve, epsilon deltas and infinite series and things like that. But I'm working on a project right now, and I happen to use some calculus for it, and so I just want to kind of illustrate like the subtle ways in which this can actually be something useful. So my goal was I wanted to create something that I could have Arduino with an accelerometer attached to it, and I could move it back and forth and try to calculate the number of cycles per minute, right? How many times it's going back and forth. And so if I use my metronome here at 60, right? It starts to dial in. It's doing a running average, and you can see it's getting pretty close to 60. Um, and if I bring this up to, I don't know, let's do 184, right? And so it's right there. It's dialing in 184. And this I tried a few sort of naive approaches to this, and it was kind of bedeviled by noise and so on and so forth. And then overnight, I woke up at one point in the middle of the night, and I was like, oh, I should just integrate, right? So what's the one line of code that makes this thing work? It's this thing right here. Okay. So really briefly, right? Um, Bovar, that's the acceleration in the direction, of this movement. So that's an acceleration, and I scale it down, and I multiply by delta t, and delta t is, the current time um, minus the last point that I took this reading of acceleration, and I multiply those, and I add it to something called bow velocity. All right. Um, and what's going on here, right? This is elementary calculus. So we know, for example, that acceleration is the derivative of velocity with respect to time, which means that dv is acceleration times dt, which means if I integrate both sides, my velocity is just the integral of acceleration times dt. Well, that's what I'm doing right here, right? Bovar over 500, that's my acceleration. Delta t, that's the amount of time that's passed. And by adding this to a running sum, I'm integrating. Because integrals are, summations, right? That's why it's written as a big drawn out S, right? It's also called a Riemann sum. And this is a number of concepts in calculus, right? It encompasses limits because my delta t is not zero. It's actually something fairly large, and this is differential calculus, and it ties in with physics and notions of motion and so on. And then this is flipping things around and using fundamental theorems and things like that to come up with velocity. So there's all these concepts related to this one line of code, right? But this line of code feels very natural to me, right? Now, did I have to know any of this stuff about calculus to type this line of code in? No. Somebody could have stood next to me and said, okay, type space BOW uppercase V, right? And I could have typed this in and gotten this program to work. But to understand why this line of code does what I need to do, which is basically do an approximation of the velocity at which this board is moving, right? That's where all of this calculus comes in. So multiple years of studying this subject. It's not about learning how to do an epsilon delta proof. It's not about learning take the exponent and move that to the front and subtract 1 from it, or the derivative of sine is cosine, or all these other things. It's the larger picture. It's the understanding of rates of change and the idea of an integral as a summation, and how we can calculate quantities by adding them up with really small time slices multiplied by the value of some function. So this was just kind of a convenient example that happened to pop up, of where I would not have thought to write this. I would not have understood why this does what it does, if not for having spent time studying calculus and working with calculus, right? And it's not about the equation; it's about the concepts. And so, yeah, what else is going on in the code here? Well, we calculate a time that's passed since our last measurement. We do this, which, estimates the bow velocity. We clip it because, this is like dead reckoning. You're not going to get a consistently correct number. Over time, it's going to drift. But I really just want to know which way this board is moving. So is the velocity positive or negative? So I clip it at 1,000. These units are effectively random. And then that gives me, this notion of velocity, and then I can use that by basically seeing if that velocity has changed since the last reading, and if it has, then I go ahead and I look at how long it's been since the bow changed direction, right? So that gives me a time which is called difference, and then I can take 60,000 and divide it by that difference, right? The difference is in milliseconds. This will give me a frequency in terms of cycles per minute, right? Or beats per minute. So, algebra here. And then I go ahead and I throw those into an array, and, freaks is an array of 10 integers. And I store it at different positions, and I increase the position. That's a circular queue. So we got algebra, we've got data structures, and we've got calculus, right? All working together here. That gives me a circular queue of the last 10 frequencies, and I just go ahead and I sample those out here and print that out. And if I want to make this a little better, what I'm going to do is I'm also going to calculate the standard deviation. I'm going to throw anything out that's say more than 1 sigma from the average. So we throw some statistics in, and that will give us a cleaner reading. So all these different disciplines, and they're coming into a few lines of code, not like thousands of lines of C, right? It's a really simple program to write. The real sort of effort here is in the kind of theoretical underpinnings that are going into informing the choice of what calculations to do here. So yeah, lots of multidiscipline crossover. It's all good stuff. So anyway, I just thought that was kind of cool, because after struggling around with some sort of elementary approaches to this, I wrote a 1-line integral function, and was able to dial in my velocities exactly. So anyway, just wanted to put that out there. Thanks. Have a good one.